Okay, well, welcome to what is one of a few videos which I'm trying to put together for this coronavirus for 2020. This first one is trying to cover off on well, really what's one of the more difficult parts of the subject, DC Circuits 104. Now whether you're doing it for Certificate 2 or indeed as part of a full apprenticeship, these concepts are you've just got to have an absolute solid grounding in them. So anyway, in this one, like I say, this is one of two presentations in relation to just topic 8 from the LMS, covering off on series circuits, and it should give you some assistance in understandings of the series circuits and so forth. We're trying to cover off in particular on this video some key concepts, and those being VT. And VT is equal to V1 plus V2 plus V3. What does that mean? We'll cover that. RT is equal to R1 plus R2 plus R3. So in a series circuit, we simply add the resistances together. Current in a series circuit, how is that sort of manipulated through a series circuit? And as you'll find out, that look, the current in a series circuit is constant throughout the circuit. And then we'll move on to talk a little bit about power, and how power is calculated. We'll have a look at some worked examples, and I mean really worked examples. Some of these examples will be out of worksheet 6, which usually comes up as part of a practical part of this topic. So I'll try to explain and have a bit of a look at how to set out the way that you work out these problems. And I must say that please try and be an awful lot neater than I've been. Look, I don't want to make an excuse or anything, but I'm trying to use PowerPoint as a whiteboard, and it's just far too small. There's just not enough space. But look, we'll have a look at how we set out. We have a look at how we check our answers and how we have an understanding that before we get to the end of some of these problems, we should be very confident that the answers that we've given are correct, and that'll come by doing more and more and more practice. We'll have a quick look at some transposition of Ohm's law. You should have probably covered Ohm's law now. V is equal to IR. Whether you use the triangle for Ohm's law, or whether you transpose it, I certainly recommend you transpose Ohm's law. But anyway, and then finally we'll have a look at some review questions, and we'll just sort of discuss some issues around that. So look, I hope you find this this video quite enlightening, I suppose. So look, let's get underway and have a bit of a look-see. As can be seen from the drawing listed above, let's try and explain what we mean by the sum of the voltages, being V1, V2 and V3, are equal to the applied voltage. Alright, so what we're saying is simply that if this voltage here was equal to 10 volts, this was equal to 20 volts, and this was equal to 30 volts, the applied voltage here would simply be 10 plus 20 plus 30, and that equals 30, 40, 50, 60 volts. Hence, we have managed to calculate VT. Now, of course, if we didn't know what this voltage here was, V3, but we did know that the VT was 60 volts, we could also calculate that 60 volts is equal to V1, which is 10, plus 20 plus something. And depending on how you want to do this, we can transpose the formula, we could do a number of different ways, but I think that if we looked at this and said simply 60 is equal to 10 plus 20, which is 30, plus what equals 60, you would, I think, realise that 30 plus 30 equals 60. So therefore, in this setup, the voltage here is equal to 30 volts. So just in conclusion, we must realise that the sum of the voltages in a series circuit equals the applied voltage. A very fundamental and key thing to realise. I hope that sorts that one out. So just to recap the previous slide, the applied voltage here would be, once I get my pen working, the applied voltage here would be equal to 10 volts plus 15 volts plus 25 volts. Shouldn't be any queries about that. So moving on to the second most important formula, and that is how do we calculate the total resistance of a circuit? If it's in series, really quite simple. We simply just add the resistors together, much the same as we did with the voltage formulas. So therefore, in this example here, RT would equal 20 plus 30 plus 50, which is 20, 30, 40, 50, plus 50 is 100 ohms. 100 ohms. And therefore we could really quite simply simplify this circuit, and it's important that you do it kind of like this at 100 ohms applied to VT. So from an electrical point of view, this circuit here is exactly the same as the circuit above here. Electrically, they look exactly the same to the supply, and this is how we simplify multiple resistive circuits. Having a look at the circuit above, and to recap, the applied voltage here is VT, the additions of V1 plus V2 plus V3. So VT is equal to 10 plus 15 is 25 plus 25 is 50 volts. Okay. RT, that's the resistance total, is equal to 20 ohms plus 30 ohms plus 50 ohms. That's 100 ohms. We've covered those in the previous couple of slides. Let's now have a look at what we do with current. Now, current being the flow of electrons, and the current which we have said here is equal to 5 amps, or it's been given to us at 5 amps. We must note that this law says that the current in a series circuit is constant. It flows around the circuit. It doesn't change in a series circuit, and it is the same current flows through that resistor as through that resistor as through that resistor. So in this example, there is 5 amps flowing through R1, R2 and R3. So that is to say that there is 5 amps here, 5 amps here, 5 amps there. So the current in a series circuit is constant. So IT equals 5 amps. The current flowing through IR1 equals 5 amps. The current flowing through IR2 equals 5 amps. And the current flowing through IR3 is equal to 5 amps. Power measured in a series circuit is simply the addition of the power of each of the resistors. So we could simply say if the power dissipated by R1 was 10 watts, R2 was 15 watts and R3 was 35 watts, just as a guess, the power total would simply be 10 plus 15 plus 35. No problems. And that would give us an answer. How to add up, of course, is 25 plus 35 is equal to, I don't know, let's say 40 watts. Okay. But let's just recap and talk about this a little bit further. I'm going to get rid of that because it's all good, but let's see if we can actually work out what the power actually is of this circuit here. So we need to work out what VT is, which we've done a number of times now, and we should simply be able to add up 10 plus 15 plus 25. That's 10 and 15 is 25 plus 25, that's 50 volts. So we should put 50 volts here. 50 volts. Cool. I would like to do it one way first. Power, which we discussed earlier, power is equal to volts times amps. There are a number of other formulas, but so if we were to work out what the power dissipated by this resistor was, we could simply say there is 10 volts across this resistor and 10 volts multiplied by 5 amps, because we know that the current in a series circuit is constant. So there's 5 amps flowing through R1 and R2 and R3. So 5 times 10, or 10 times 5 is 50 watts. So this resistor here is displacing 50 watts. Okay, so PR1. What's the power in PR2? Well, the voltage across R2 is 15 and the current flowing through it is 5. What's 5 times 15? Well, it's 50. 10 times 5 is 50. 5 5s are 25. That's 75 watts. 75 watts through that resistor. Now the wattage, of course, is a measurement of energy. So it's in a resistor, it's purely given off as heat. So the heat given off by R2 is 75 watts. Okay, so the power in a series circuit is that R3. We're trying to now work out what it is in R3. In R3, use all these pretty colours. R3, the voltage across R3 is 25 volts multiplied by the 5 amps. Oh, now we're starting to get a bit hard. 25 times 5 is 4 is 100, 125 watts. So 125 watts. Now, this formula here is saying to us that we simply need to power total is equal to P1 plus P2 plus P3. So we could, that's not so good, Tom. I need to go to home, scroll down the page a little bit. No. Okay, running out of room. Okay, so PT is equal to 50 watts plus 75 watts plus 125 watts, and that equals 125 plus 75 is 250 watts. We might just remember that. That's one way of being able to do it. It's a pretty long way of being able to do it, but the way that we should be doing it, I think, or another way of doing it, is let's just make a little bit of space here and give us a new page. If we were to simplify the electrical circuit like we did previously, and instead of doing all of that maths above, we could do this. Both ways of doing it are correct, but if we were to calculate what RT is, we covered this earlier, RT is simply the additions of 20 ohm resistor, a 30 ohm resistor and a 50 ohm resistor. So 20 plus 30 is 50, plus 50 is 100 ohms. We could redraw this circuit to equal a 100 ohm resistor. We are given 5 amps flowing through this resistor, and we calculated previously that we had 50 volts across that resistor. Now, power is equal to volts total, amps total. The voltage total is 50 volts multiplied by the total current is 5. 5 5s are 25 and add a 0, 250 watts. That answer there is the same as that answer there. So there are two ways of being able to calculate the power, and as we move on you will find that the best way to solve these problems is to simplify the circuit down into a smaller circuit and do your calculations. This is the game of chess that I talk about. Okay, let's have a look at the circuit which we've got listed above here, and let's see if we can simplify this circuit to try and find total resistance, the voltages across all the resistors, and the current through all the resistors, and the total current. So the first thing we need to do is simplify the circuit. So our first little drawing needs to be a circuit with one resistor in it. We have 10 volts and RT equal to R1 plus R2 plus R3, and that's 20 plus 19 plus 20. 20 and 20 is 40, 59 ohms, 59 ohms. So 59 ohms. Okay, RT equals 59 ohms. Okay, let's just get rid of that for a minute. Let's now see if we can calculate the current flowing through the circuit. So I is equal to V on R. Just let us have a look at a moment. V is equal to IR. That's Ohm's law. I'll just spend a moment to go transpose this formula. I am trying to work out I, the current. So what I do is I divide both sides by R. The R's cross out here. I'm left with I on its own is equal to V on R. So V is divided by R is equal to I. Of course, we normally write that around the other way. So, all good. That all being said, we'll just remove that just for clarity. So I've just transposed that formula there to that formula there. Now, that's cool. So, over here we have the voltage across the resistor is 10 volts divided by the 59 ohms. That is equal to 10 divided by 59 is equal to 0.1695 amps. Or, if we move the decimal place 3 places, it'd be 169.5 milliamps. Either of those two answers are correct. So let's go 0.1695 amps. Okay, cool. So we'll work that out. You can see why you need a larger piece of paper, but anyway, there we go. IT equals 0.1695 amps. Cool. Right, let's now try and work out what VR1 is, VR2, VR3. Okay. Well, Ohm's law states that the voltage is equal to IR. The current is 0.1695 multiplied by the resistance of 20 ohms. So I'm trying to work out the voltage across this resistor. That's what I'm trying to work out. So I have to use the current through that resistor and the resistance value of that resistor. Cool. So that is equal to 0.1695 multiplied by 20 equals 3.39 volts. 3.39 volts. Cool. Let us have a look at the the voltage, across this resistor. V is equal to IR. Probably should go VR2 IR2 and R2. The current is the same through the second resistor and the third resistor, because we covered it earlier that the current in a series circuit is constant, multiplied by the resistance value, which is 19 ohms. Let's have a look. 0.1695 multiplied by 19 is equal to 3.2205. Let's not worry about that. So that's 3.22 volts, and you would expect it to be quite similar because 19 ohms is very close to 20 ohms, but anyway. VR3 is equal to IR3 times R3. You note that we're working out, trying to work out the voltage across this resistor. You note that this is a 20 ohm resistor, so was R1, so you would think they would be the same voltage, and of course they are. So the voltage across R3 is the same as across R1, which is 3.39, because if we follow the maths here, 1695 multiplied by 20 is 3.39 volts. Alright, now something we should do, because we know that Vt is equal to V1 plus V2 plus V3, I'd just like to check our answers. 3.39 plus, getting a bit messy here, Tom. 3.39 plus 3.22 plus 3.99 is equal to Vt. Let's just add those up for a moment. .39 plus 3.22 plus 3.39 is equal to 10 volts. Now you can see that 10 volts is the same as the supply voltage. So all of these answers have been checked and we know that they are correct. Alright, so having said that, let's just clear a bit of a page and let's see if we can't work out the currents through the circuit. Oh yeah, we've done that, haven't we? We've actually worked out the current through the circuit. If I look here, we calculated the current through the circuit here. Alright, so that being the case then, IT, yep, there it is, IT is there, cool. So what is the current through IR1 and IR2 and IR3? Well, if you remember, the current in a series circuit is constant, so 1.695 amps, 0.1695 amps, 0.1695 amps. So that should sort out the complete solving of that circuit. Okay, straight out of question sheet, or should I say worksheet 6, question 6. This question is asking for you to find the total resistance, the voltage drop across all 4 resistors, the total power taken by the circuit, and the total power taken by R3. Okay, so what do we know? And I'm just looking at it now. We know that we've got 48 volts supplied, 4 amps flowing in the circuit. We've got 0.6 of an ohm, 3.8 ohms. Aha, we do not know the ohms here, and 2.2. So we need to, we've got 2 unknowns here. This is the game of chess I talk about. So what we need to do here, I think a fair way to start this problem would be to calculate the voltages across all of these resistors. And when we know that, we can certainly calculate the voltage across this resistor because we know the current through it and we know its resistance value. The same with this one, we can calculate the voltage across this resistor because we know the current and we know the resistance value. We don't know how to work the voltage out on this resistor because we don't know its value of resistance. However, we do know that if we calculate the voltage for this one, and this one, and we already know this one, then we can simply add these up to equal 48 volts, and we will know what the resistance value is here. So let's go ahead and do that. So VR1 is equal to I times R. Current is 4 amps and the resistance is 0.6. Just because there's a decimal point there, I'm not going to guess it right at the start of a recording. That'd be handy. 0.6 times 4. 0.6 times 4 is 2.4 volts. Cool. VR2 is equal to IR. Current is 4 and the resistance value is 3.8. So 4 times 3.8 is equal to 15.2 volts. VR3, and of course we can use the current, as you are now aware, is constant at 4 amps all the way through the circuit. That's the problem. Don't know what that is, so I can't work that one out. Okay. VR4, 4 times 2.2, 4 times 2.2 is 8.8 volts. Okay, so 8.8, 15.2, 2.4 equals 48. So what is 2.4 plus 15.2 plus 8.8? 8, 9, 10, 14. 8, 9, 10, 11, 12. Well, I just gave you a demonstration how not to add up. Let's use the old calculator, eh? 2.4 plus 15.2 plus 8.8. Okay, that equals, if we add that plus that plus that, it equals 26.4 volts. And we know that VT is equal to V1 plus V2 plus V3 plus V4. So therefore, if we muck around with this formula and so on, 48 minus 26.4 equals 48 minus 26.4, 21.6. The voltage across here is 21.6 volts. And that's because 8.8 plus 21.6 plus 15.2 plus 4.2 equals 48 volts. So we now know all the voltages across all the resistors. Let's get a little bit of clear space and see if we can work out the resistance of R3, and we should be able to do that now because we know the voltage across it. So we're trying to work out the value of resistance now of R3. R3 is equal to the voltage on the current. Now, just let's spend a moment here. V is equal to IR, just showing you that Ohm's law is there, and we're trying to calculate R. I want R. So if I divide this side by I's cancel out. Let me just do that again because it's not very clear. It's not very clear at all, that. So V is equal to IR. I am trying to find R. I want R to be the answer. So I divide both sides by I. These cancel out. V on I equals R. And like we said before, we don't like to have it that way around, so we just move it around this way. We're just moving the R from there to there, and all of this from there to there. Okay, cool. So, that being the case, there is our new formula to find our resistance. Okay, and all I've done is transposed that formula into that formula there. Okay, that being said, the voltage across R3 is 21.6. The current through that circuit, which is constant, is 4. Therefore, R3 is equal to 21.6 divided by 4 is 5.4 ohms. So that gives us 5.4 ohms. Can I write that in there somewhere? 5.4 ohms. Okay, so we have calculated all the bits and pieces to do with that answer there. The voltage drop across all the resistors. We now need to let's have a look and see if we can find the total resistance. So that should be quite easy. Previously we talked about RT equals R1 plus R2 plus R3 plus R4 and so on and so on. This is 0.6 plus 3.8 plus 5.4, that was our missing one, and 2.2. What does that equal? 0.6 plus 3.8 plus 5.4 plus 2.2 equals 12 ohms. So we could redraw this circuit with a 12 ohm resistor connected to a 48 volt supply. RT, we have calculated here this now at 12 ohms. Okay. It's now asking for the power. I think it's the total power taken by the circuit. Alright, well we know that there's 4 amps flowing in here, because that was given here. Power is equal to volts times amps. The total voltage, 48 volts, multiplied by the current in the circuit, which is 4 amps. 48 times 4. 48 times 4 is 192 watts. So it's 192 watts of electrical energy dissipated in this resistor here. Or we could, if you wanted to, calculate the power dissipated by R1, R2, R3, R4, and we could add those up and you would have the same, you would come to the same answer. Okay, total power dissipated circuit done, 192 watts. So the last question is power taken by R3. This is R3 here. So power is equal to volts times amps, and this is PR3, R3, R3. So the voltage across R3 is 21.6 volts multiplied by the current in the circuit, and the current in the circuit is constant. It doesn't change, it goes through every resistor. It's 4 amps. So 21.6 multiplied by 4 equals 86.4 watts. There we go. I believe that answers all the questions for question 6 in worksheet 6. Review questions. Let's just have a look here. Ammeters are connected in series in a series circuit. Is that correct? An ammeter uses or measures the current or the electron flow. So an ammeter would be connected in series as the electrons have to flow through the ammeter. So the answer to that would be would be true. Would be true, and there is no true. Ammeters are connected in parallel. They're not connected in parallel. No, they're connected in series, so an ammeter would be connected in series with a load. That would be an ammeter. So the answer would be, indeed, be false. Okay, question number 2. An open circuit in a series circuit will see high currents flow. Well, what do you think about that one? An open circuit, so if we had a switch and it was opened, there would be no current flow, so that must also be false. Okay. Series circuits are limited to 10 components. Well, no, if you think of the Christmas tree that you have every Christmas, you have a light bulb, another light bulb, another light bulb. I don't know how many light bulbs you have in your Christmas tree, but there's an awful lot of them, and you might connect that to 240 volts and you might have 240 light bulbs, in which case each light bulb would be 1 volt. Anyway, so certainly series circuits can have many more than 10 components, so that would be false. Question 4. Current is the same in all parts of a series circuit. That should be true, and there it is, because we know, as we've explained earlier, that the current in a series circuit is constant. In other words, the current flowing in a series circuit always flows around through all the components. Getting a bit hard to draw on this, but anyway, but every component has that current flowing through it. Anyway, we explained that earlier. Adding resistors in a series circuit will reduce the current. That is correct, because if we have a resistor in a circuit and we add another one, at the end of the day the resistance value will go up because R1 equals RT equals R1 plus R2 plus R3. So if we add another resistor into a circuit, the resistance value goes up, and we know that the current will reduce if the resistance is increased. So that answer is true. Multiple choice question. The total resistance in a series circuit is equal to the largest resistor value, lowest resistor, sum of the resistors in series, the average of the resistors. Well, we should know, and we have explained, that RT equals R1 plus R2 plus R3. So that's a bit scrappy, but that is C. The sum of the resistor values connected in series. Yeah, so the resistance of a series circuit is equal to the sum of the resistors. Okay, so that is C. Oh, there you go. There's the answer right there. Okay, the sum of the voltage drops across the resistor connected in series is equal to the sum. Well, VT equals V1 plus V2 plus V3, yeah? So the sum of the voltage drops across resistors connected in series equal to the applied voltage, and look at that, there's the answer there. Okay, cool. An open circuit in a series circuit will cause the current to reduce to 0. It's just like opening a switch. So an open circuit is like a switch being, that's the open circuit bit. If the switch, sorry, I'll just change this. If the switch is closed. That's closed, that's normally closed, that's normally open. That current will be allowed to flow around there. In this case, there cannot be any current flow because the switch is open. So an open circuit in a series circuit will cause current to rise, definitely not. Current to remain the same, definitely not. Current to stop. There it is, C. C, there's the answer. I'll put the next number of questions up. Have a go at them. The answers are given, but try and work through them and see how you go.